In 1974, Stephen Hawking discovered something impossible. Black holes, the darkest objects in the universe, where gravity is so strong that nothing escapes, aren't actually black. They glow, they evaporate, they radiate particles into space, and over trillions of years, they disappear completely. This wasn't just a minor correction. It shattered everything we thought we knew about black holes, information, and reality itself. Because if black holes can destroy information, then the laws of quantum mechanics are broken. And if they can't, then something even stranger is happening. Welcome to the black hole information paradox, where Einstein's relativity and quantum mechanics collide, and nobody knows who wins. Let's start with what black holes are. When a massive star runs out of fuel, it collapses. If it's massive enough, at least 3 times the sun's mass, the collapse doesn't stop. Gravity crushes it into a point of infinite density called a singularity. Around that singularity is the event horizon, the point of no return. Cross it, and gravity is so strong that even light can't escape. That's why they're called black holes. They're black because nothing, no light, no information, no matter, can ever get out. Or so we thought. Einstein's general relativity predicts black holes perfectly. The equations show exactly how spacetime curves around massive objects, and when you push those equations to the extreme, infinite density, infinite curvature, you get a black hole. The math works. Observations confirm it. We've detected black holes through gravitational waves when they collide. We've photographed the event horizon of the supermassive black hole in M87. Black holes are real, no question. But here's the problem. Quantum mechanics says information can't be destroyed, ever. This is the principle of unitarity. Quantum states evolve in reversible ways. If you know the quantum state now, you can calculate the past and predict the future. Information is conserved, always. But black holes seem to violate this. When something falls into a black hole, a star, a planet, it carries information. The arrangement of atoms, quantum states, everything that makes that object unique. Once it crosses the event horizon, that information is gone, hidden behind the horizon. And if the black hole evaporates completely, which Hawking says it does, then the information is destroyed. Poof, gone forever. That breaks quantum mechanics. And that's a crisis. Because quantum mechanics is the most tested theory in physics, it's never been wrong. So either black holes destroy information and quantum mechanics is incomplete, or information isn't destroyed and something weird is happening. Hawking's discovery came from combining quantum mechanics and general relativity in a new way. Near the event horizon, quantum fluctuations occur constantly. Empty space isn't actually empty. It's filled with virtual particle pairs, a particle and antiparticle that pop into existence, exist briefly, then annihilate each other. Normally, this happens everywhere, and you never notice. But near a black hole's event horizon, something strange can happen. One particle of the pair falls into the black hole, the other escapes. To an outside observer, it looks like the black hole is emitting particles. This is Hawking radiation. The escaping particles carry energy, and since energy and mass are equivalent, E/mc2, the black hole loses mass. Over time, it evaporates. A stellar mass black hole would take 10^67 years to evaporate completely. That's vastly longer than the current age of the universe. But a tiny black hole, say, one the mass of a mountain, would evaporate in seconds, releasing energy equivalent to millions of nuclear bombs. Primordial black holes from the early universe might be evaporating right now. But here's the kicker. Hawking radiation is thermal. It's random. It doesn't carry information about what fell into the black hole. If you throw an encyclopedia into a black hole, the radiation coming out is just heat, random particles with no structure. The information in the encyclopedia is lost. This is the information paradox, and it's been driving physicists crazy for 50 years. Hawking himself initially believed information is destroyed. He argued that black holes are exceptions to quantum mechanics, but that's unsatisfying. Exceptions are red flags. They usually mean you're missing something. So physicists searched for alternatives. One idea: maybe information isn't destroyed. Maybe it's encoded in the Hawking radiation in subtle ways we don't understand yet. The radiation looks random, but maybe there's hidden structure, correlations too complex to detect with current methods. This is the black hole complementarity proposal. It suggests information is both inside the black hole and in the radiation. From the perspective of someone falling in, information crosses the horizon and is lost. From the perspective of an outside observer, information is encoded in the radiation and never truly enters. Both perspectives are valid. They're complementary. Like wave-particle duality in quantum mechanics. The particle is both a wave and a particle depending on how you measure it. Similarly, information both enters the black hole and escapes depending on your reference frame. This preserves unitarity without violating relativity. But it's weird. And it leads to the firewall paradox. Here's the problem. If information is encoded in the Hawking radiation, then particles escaping the black hole must be entangled with particles that fell in earlier. That's how information gets out, through quantum entanglement. But entanglement is monogamous. A particle can't be maximally entangled with two different things. Yet for Hawking radiation to carry information, escaping particles must be entangled with both the infalling matter and with each other. That's impossible. Unless something breaks the entanglement. Physicists propose that at the event horizon, a firewall forms, a wall of high-energy particles that burns anything trying to cross. This saves information, but it violates the equivalence principle, Einstein's idea that free fall should feel smooth, with no special effects at the horizon. If there's a firewall, falling into a black hole isn't smooth. You'd be incinerated instantly. That contradicts general relativity. So we're stuck. Save quantum mechanics, break relativity. Or save relativity, break quantum mechanics. Pick your poison. Another proposal: holography. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary. Like a hologram, a 2D surface that contains a 3D image. Applied to black holes, this means information that falls in is encoded on the event horizon itself. The horizon acts like a hard drive, storing data. As the black hole evaporates, that information is released in the radiation. Physicist Leonard Susskind championed this idea, and it led to a remarkable discovery. Black holes have entropy. Entropy measures disorder, or information content. The entropy of a black hole is proportional to the area of its event horizon, not its volume. Bigger horizon, more entropy, more information storage. This is the Bekenstein-Hawking entropy formula. It connects thermodynamics, quantum mechanics, and gravity in a profound way. And it suggests the universe might be holographic. Our 3D reality might be a projection from information encoded on a 2D boundary at the edge of space. This sounds like science fiction, but the holographic principle is taken seriously. It's central to string theory and the ADS-CFT correspondence, a mathematical equivalence between a gravitational theory in one space and a quantum field theory in a lower dimensional space. If the universe is holographic, then reality as we experience it, 3 dimensions, objects, events, is emergent. The fundamental layer is 2D information. We're living in a projection, and black holes are the key to understanding this, because they're the ultimate information processors. They encode, store, and release information in ways we're only beginning to understand. But we still don't have a complete answer. Does information escape? If so, how? If not, why does quantum mechanics break? Some physicists think the answer requires a theory of quantum gravity, a unified framework that merges general relativity and quantum mechanics. String theory is one candidate. Loop quantum gravity is another. Both predict modifications to black hole behavior at the Planck scale, the smallest possible scale where quantum effects dominate. Maybe at that scale, singularities don't exist. Maybe space-time itself is granular, made of discrete units. Maybe black holes aren't smooth event horizons, but fuzzy quantum objects called fuzzballs. If true, there's no singularity, no information loss, no paradox. The information is always accessible, just scrambled in complex ways. Then there's the idea that black holes leak information through subtle quantum effects we haven't detected yet. Physicists have calculated that late-time Hawking radiation, emitted near the end of a black hole's life, contains complex correlations that carry information. Early radiation is thermal and random. But as the black hole shrinks, quantum effects intensify, and information encoded on the horizon gets transferred to the radiation. By the time the black hole vanishes, all the information has escaped. It took a while, but nothing was destroyed. Unitarity is preserved. This is called the Page curve, after physicist Don Page. Recent calculations using tools from string theory and holography support this. Hawking himself, before his death, revised his position. He conceded that information probably escapes, though he never fully explained how. But even if information escapes, the paradox reveals something deeper. Black holes are laboratories for testing the limits of physics. They force us to confront the incompatibility between relativity and quantum mechanics. And they hint at a more fundamental theory, one where space-time isn't fundamental, but emergent, where information is primary, where the universe operates like a quantum computer, processing information at every level. Some physicists, like John Wheeler, believed information is the foundation of reality. It from bit. Matter, energy, space, time, they all emerge from information. And black holes are the ultimate proof. Let's talk about what it would be like to fall into a black hole. From far away, you'd see it as a dark sphere, warping the light of stars behind it. As you approached, tidal forces would stretch you. Gravity is stronger at your feet than your head, so you'd elongate, a process called spaghettification. For a stellar mass black hole, this happens before you reach the horizon. You'd be torn apart. But for a supermassive black hole, like the one at the center of our galaxy, tidal forces at the horizon are weak. You could cross without noticing. From your perspective, nothing special happens. You pass through smoothly. But you can't escape. And from outside, time dilation makes you appear to freeze at the horizon, never quite crossing. To you, seconds pass. To an outside observer, you're frozen forever, redshifted into invisibility. This is the complementarity again. Both views are correct, but they're irreconcilable. You either burn in a firewall or pass through smoothly. Physics doesn't know which. Now let's consider detection. Can we observe Hawking radiation? Not yet. It's incredibly weak. For a solar mass black hole, the temperature is about 60 nanokelvin, far colder than the cosmic microwave background. The radiation is drowned out by ambient noise. Only tiny, primordial black holes would be hot enough to detect, and we've never found one. But that might change. Future telescopes might detect gamma-ray bursts from evaporating primordial black holes, or we might create micro-black holes in particle accelerators. If we do, they'd evaporate instantly in bursts of Hawking radiation. That would confirm the theory, and it would be Nobel Prize worthy. There's also the question of what happens at the singularity. General relativity predicts infinite density and curvature. But infinity is a red flag in physics. It usually means your theory breaks down. Quantum mechanics doesn't allow true infinities, so the singularity probably isn't infinite. It's a quantum object, a region where quantum gravity dominates. We don't have the math to describe it yet, but when we do, we'll finally understand what's at the heart of a black hole. Maybe it's a Planck star, a quantum bounce that prevents total collapse. Maybe it's a wormhole to another universe. Maybe it's something we can't even imagine yet. Black holes also connect to cosmology. Some theories suggest our universe was born from a black hole in a parent universe. The Big Bang was the interior of a black hole expanding. If true, then black holes create new universes, and our universe might create countless universes inside its own black holes. This is the black hole cosmology hypothesis. It's speculative, but it's consistent with what we know, and it offers a naturalistic explanation for why our universe exists. Not design, not chance, just physics, black holes reproducing, universes evolving. A cosmic selection process where universes with physics favorable to black hole formation produce more offspring universes. Finally, let's address the philosophical implications. If black holes evaporate, then nothing lasts forever. Stars die. Galaxies fade. Black holes vanish. Even the universe itself might end in heat death, maximum entropy, no structure, no life, no thought. Is that depressing or liberating? Some find comfort in permanence. Others find meaning in impermanence. Buddhist philosophy embraces transience. Everything changes, nothing lasts, and that's okay. Maybe black holes teach us the same lesson. Enjoy existence while it lasts, because eventually, everything, matter, energy, information, returns to the quantum foam from which it came. The universe forgets, and that's strangely beautiful, not tragic, just complete. So where does this leave us? Black holes aren't black. They radiate, they evaporate, they challenge our understanding of information, space, and time. We still don't have all the answers, but we're closer than ever. Quantum gravity, holography, string theory, these are the tools we're using to solve the puzzle. And when we do, we'll understand not just black holes, but the fabric of reality itself. Because black holes are mirrors. They reflect back our deepest questions about existence. And maybe, just maybe, they hold the answers too. So the next time you think about a black hole, don't imagine darkness. Imagine a glowing quantum object, radiating information, dissolving slowly into the cosmos, leaving behind only the memory of a mystery that pushed humanity to the edge of understanding. And then, beyond.